Okay, now let's solve the same question where sigma square unknown. So in this case we have a nuisance parameter sigma square, so we have to also take care of this unknown parameter by finding its MLE under the null hypothesis and under the whole parameter space. And parameter space actually defined by our hypothesis. Okay, so the same hypothesis we have mu equal mu 0 versus mu not equal to mu 0, and let's assume that we have a random sample of size n, and let's derive the likelihood ratio test, or GLRT, generalized likelihood ratio test of size alpha. Okay, so let's first define the parameter space. So the actual parameter space that we have contains all mu values, because when we combine null and alternative hypothesis parameter spaces, then we will see that it covers all parameter space basically, and sigma square is greater than 0. And when we consider the null space, so our mu only take mu 0, and our sigma square is again positive, so we don't have any constraints on that one. So based on that, we have to find the region. Okay, so if you draw the region that we have in terms of mu and sigma square, then let's say this is our mu 0, and this point will be our gamma 0, and this parts will be our omega 1, and the whole space basically gives us so it's in terms of sigma square, we have to consider all positive sigma squares. Okay, so let's try to find the likelihood ratio, but to be able to find the likelihood ratio, we need to find in the denominator the maximum point where mu and sigma square is replaced. So we have to find the maximum value of the likelihood function in terms of mu and sigma square, where our mu is in this region and sigma square is positive. And for normal, actually we know the MLE of mu and sigma square, since it covers our parameter space covers the whole range, so we don't have to think about another region. You will see in the exponential example you have to consider other regions. If you have a one-sided hypothesis, we have to consider that. So our mu hat is x bar, and our sigma hat square is s square, but s square is defined by unbiased, not biased case, actually by divide by n. This is the point that we have. So this means that our maximum likelihood obtained at x bar and s square. Okay, so when we write the formula here, we will get, for a random sample of size n, we will have this, and we have e to the minus summation xi minus x bar whole square divided by this should be s square, because we have to replace all the unknowns, s square. So if we focus on this part, you will see that we have summation xi minus x bar whole square divided by n times summation. Oh, I have n there, so it's not n. So let me erase this and this. So it should be 2. Okay, so we have 2 times summation xi minus x bar square over n when we replace s square formula. So these quantities will cancel out, and we will have n over 2. So if we write the whole maximum likelihood under the whole parameter space, so we will end up with this formula. Again, I wrote sigma s square n over 2 e to the minus n over 2. Okay, so let's try to find the numerator part. So this is the maximum likelihood point under the case that for mu and sigma square, where mu equals mu 0 and sigma square is positive. So basically, since mu only takes value mu 0, our maximization should be on sigma square only. Okay, so let's find the maximum likelihood estimator for sigma square, where mu is replaced by mu 0. So for sigma square under this condition, we have 2 pi sigma square n over 2 e to the minus summation xi minus mu 0 to sigma square. Take the ln to find the MLE. Oops. Okay, and we have the rest. Okay, so taking the derivative with respect to sigma square. Mu 0 square over 2 sigma to the 4 equate this to 0. So we will get s square as, or let me don't use s square notation for this. Let me use this summation x I minus mu 0 whole square divided by n. Okay, so this means that our maximum point of under the null space will be the case that we have mu 0 and sigma square. When we replace it, so we will have 2 pi sigma 0 hat square n over 2 e to the minus summation xi minus mu 0 whole square divided by 2 sigma 0 hat square. Okay, again, let's focus on this part. So we have summation xi minus mu 0 whole square divided by 2 times what is sigma 0 hat square xi minus 0 square over n. Again, these terms cancels out and we have n over 2. Okay, so our maximum point will be 1 over 2 pi sigma 0 hat square n over 2 e to the minus n over 2. Okay, so now our likelihood ratio, generalized likelihood ratio, will be lambda, where we will get the ratio of these. Okay, and in the numerator we have this one, n over 2 e to the minus n over 2, and under the denominator we have s, we name it s square, n over 2 e to the minus n over 2. So these cancels out, 2 pi's cancels out, and we will end up with s square over sigma 0 hat square n over 2. Okay, so now we have to write this likelihood ratio, generalized likelihood ratio, in terms of one statistic. Right now we have just s square and sigma 0 square, and under the null hypothesis we cannot define a good statistic. So let's try to open up and then get a compact form for this. So let's open summation xi minus x bar whole square divided by n, and summation xi minus mu 0 square over n. So n's will cancel out. So here, if you notice here, we have summation xi minus x bar square. So by adding some constants to the numerator, we can add mu 0 plus minus mu 0 term, or we can add xi minus x bar term in the numerator part. So making this part like that, so it might be easier to put x bar plus minus x bar terms under the denominator. So we will end up with a known distribution actually. But you can try the other way, so putting mu plus minus mu 0 this part. But let's try this. So we have summation xi minus x bar whole square divided by summation xi minus x bar plus x bar minus d0 square and over 2. Okay, so if we do it like that, so you will see that we will have xi minus x bar whole square divided by summation xi minus x bar whole square. So 2 times summation xi minus x bar times x bar minus mu 0 will be 0, because summation xi minus x bar term will be 0. So we will end it up with n times x bar minus mu whole square. Okay, so getting rid of the summation xi squares and getting more compact form, we have 1 plus n times x bar minus mu 0 square over summation xi minus x bar whole square and over 2. So so we observe a statistic here, which is this one, and now we have to find the distribution of n times x bar minus mu 0 square and this one. So this will be our statistic. Okay, and you will see that actually it is actually very well known statistic. So by naming that this t0 square over n minus 1, we will derive the distribution of t0. Okay, since I have some technical problems, I had to record this, so we will continue. So you will see the continuation of the solution in the next video. Okay, see you guys.